All right, let's talk about something called computational thinking. And hey, before you click away thinking, this sounds like it's for programmers, just hold on. It's not. It's actually a super powerful way to solve problems, any kind of problem really, by learning to think with the kind of structure and logic that a computer uses.
I mean, think about it. You solve little puzzles all day long. When you scan a crowded bookshelf for one specific title, or when you sort a huge pile of laundry. Your brain just kind of does it. It's using intuition. It's recognizing patterns. But here's the real question. Could you write down the exact step-by-step instructions for a machine to do it? A machine that has absolutely zero intuition? Well, that's the whole challenge we're diving into.
So, first things first, we've got to break down the huge difference between how our brains work and how a computer thinks. Understanding this gap is pretty much the key to the whole thing.
We run on intuition and patterns. If I asked you to go find the salt in a kitchen, your brain would instantly process the whole room, think about where spices usually are, and you'd probably find it in seconds. A computer? No way. It needs what the source material calls a stepwise approach. You'd have to tell it literally, go to coordinate XY, open cabinet number 3, scan shelf 2 from left to right. Is the label SALT? Every single step has to be spelled out perfectly.
And this is the funny thing about computers, isn't it? They have incredible power. They can do a boring, repetitive task a billion times without ever getting tired or making a single mistake, which is definitely an upgrade from us humans. But, and this is a big but, without a perfect, crystal clear plan, all that power just sits there, completely useless. Computational thinking is how we create that plan.
So, how do we actually create that perfect plan? You might think it starts with a bunch of complicated code on a screen, but nope. Surprisingly, it often starts with something way simpler. A pen and paper. We need to literally draw a blueprint for our logic.
And this is what that blueprint looks like. It's called a flowchart. And what's really cool is that this image is taken right from a student's notes on this very topic. This is the visual language we use to map out our thoughts. It's how we take a fuzzy idea that's floating around in our heads and turn it into a concrete map of actions and decisions that a computer could actually follow.
And the system itself is actually pretty simple. You have these oval shapes, the terminals, that just show where the process starts and ends. Then you have rectangles, which are your process steps. Those are the actions, like add a number or open a file. And the most important one, you've got the diamond. This is the decision block, where you ask a simple yes or no question that tells the process which path to take next.
This quote from the source material really gets to the engine of the whole operation, the iterator. You see, the computer's real superpower is repetition. It can do the same simple thing millions of times without a single error. So our plans, our flowcharts, have to be designed to take advantage of that amazing strength.
To build these logical blueprints, it turns out we only need 3 fundamental tools in our thinker's toolkit. Let's break them down.
First up, as we just mentioned, is iteration. This is just the power of repetition. Imagine you had a stack of 1,000,000 library cards, and you had to check every single one for an overdue stamp. You'd go crazy, right? But a computer can just go through them one by one, without ever getting bored, without ever losing its place. That's the heart of all of this.
Okay, but if you're iterating through 1,000,000 things, how do you remember anything? You need a memory, and that's exactly what variables are for. You can think of them like little sticky notes for the computer. It can write down a piece of information, like a running total or a customer's name, and then come back and check or update it later. It's just a place to store stuff.
And third, we have filtering. This is the logic that happens inside that decision diamond. It's all about applying a condition to your data. You know, asking a question like, is this number greater than 100? Or is this customer city Chennai? Filtering lets the program look at the data and decide what to do next based on the rules we gave it.
Here's a perfect example of all 3 tools working together. This flowchart is designed to add up the total amount spent by one customer, Ahmed. So it iterates through every single bill. Inside that loop, the decision diamond asks one simple question. Is the customer's name Ahmed? That's the filter. If the answer is yes, it adds the bill amount to a variable, our running total. If no, it just skips it and moves to the next bill. See? Iteration, variables, and filtering all working in perfect harmony.
Okay, so we've got our tools. Now let's put them together to tackle a problem that's a little more complex. And by doing this, we'll see the very first pillar of computational thinking in action, something called decomposition. It's just a fancy way of saying we're going to break a big problem into smaller, more manageable pieces. Here's our challenge, taken right from the source material. We've decomposed the bigger goal into a very specific, answerable question. Out of a big list of students, how can we find the total marks for only the students who are both female
and from the city of Chennai.
And here we have our algorithm design. This flowchart is our algorithm. It iterates through every student, one by one. But notice the structure here. It's nested. First, it filters by asking, is the student female? If the answer is no, it just moves on. But if it's yes, it then asks a second question. Is the city Chennai? Only if the answer is yes to both questions does it finally add the marks to our total.
And this is what that logic looks like when you apply it to the actual data. The program just marches down the list. Bhuvanesh? Nope. Harish? Nope. Then it gets to Rita. Is she female? Yes. Is she from Chennai? Yes. Boom. Her 173 marks are added to the total. The algorithm we designed gives the computer the perfect, repeatable logic to just chew through this entire list.
Now, all this planning and drawing is fantastic, but how does it actually become a real program that a computer can run? Well, here's the amazing part. By creating this logical plan, we've already done about 90% of the work.
Take a look here. On the left is something called pseudocode. That's basically our logic written in plain English. On the right, that's actual Python code. Now they're solving two different problems, but just look at the structure. They both create a variable at the start, they both use a loop for iteration, they both update that variable inside the loop. The programming language itself, that's just syntax. It's like a final translation step. The real work, the computational thinking, was already finished when we made the plan.
So what have we really been doing this whole time? Well, we've been practicing the 4 pillars of computational thinking. When we broke down that Chennai problem into smaller pieces, that was decomposition. When we created a reusable process for checking each student, that was pattern recognition. When we decided to ignore unimportant data like the student's age, that was abstraction. And that flowchart we designed, that was our algorithm. It's a full framework for clear, logical problem solving.
And this framework, it goes way beyond just coding. It's a tool for clarity, whether you're planning a big project for work or just trying to organize your errands for the week. It forces you to stop, take a breath, and build a logical, repeatable plan before you just jump in. So I'll leave you with this question. What everyday problem will you solve differently now?